All right, we're back here at page 3 of the DBA review packet. Question 8. 25-gram piece of iron at 888, added 100 milliliter beaker full of water. Identical 25-gram piece of iron, 888 to 500. Your only difference, 500 versus 100. Will the water in the two beakers rise to the same temperature? No. Okay. Why? If not, which no, which beaker containing water would reach the highest temperature? Well, the 100 milliliter is going to reach the highest temperature, because if I have a beaker of only 100, and then I have a beaker of 500, and I'm adding the same piece of metal to it, okay, same size piece of metal, well, this one is going to increase that temperature a lot more because there's a lot less of that, okay? So the 100 milliliter beaker, that's going to be able to raise that temperature more, okay? Write the equation used to calculate heat absorbed or released. Label and describe each of the variables. So that's Q equals MC delta T, or you can write it as Q equals MC TF minus TI. Q is heat. That's measured in calories or joules. M is your mass. C is your specific heat capacity. That's measured in calories or joules per gram degree Celsius. And then we'll kind of move over here. T is temperature, obviously. TI equals temp initial. And then TF equals final. Remember, it's always TF minus TI. F comes first on the alphabet, so that's how you remember to put it first in that equation also. Okay, onto these. How much heat will 1.2 grams of water lose if its temperature changes from this to that? Well, let's set this equation up using this Q equals MC delta T equation. I'm solving for heat, so I'm solving for Q. All right, I have a mass of 1.12 grams. I do not have a C, but it's understood that water has a specific heat of 1 calorie, okay? And then I have my temperatures. So 31.2 to 11.1, meaning I went from this to that. This is going to be my final. So 11.1 minus 31.2. Okay, so now I have all that up. All I'm doing is plugging that into my calculator. When I plug that in, I get a final answer of 22.512 calories. It's in calories because it's heat. Okay, moving on to the second portion here. I'm working in joules. It doesn't matter. It's the same thing as calories. It's just a heat unit. So I'm dealing with 1250 joules of energy. Pure silver. I'm heating from this to that. Calculate the mass. I want the mass on this one. So if I was to set this one up, Q equals 1250. M is what I'm solving for. C, it tells me my specific heat of silver is 0.235, and then TF equals final is 15.2, TI equals 12. Plug all this in. Oh, sorry, I'm looking at the wrong problem. Do it over here. 1250 equals, solving for M, 0.23, 15.2 minus 12. Okay, I'm going to multiply these together. Well, first I'm going to subtract these two, multiply that by 2.3, take that product, 1250 divided by that product, and I'm going to get 1662.23 grams. Okay, moving on to this last one, I'm going to deal with, I've got 125.6 grams. Temperature final, temperature initial. I have that just for my energy. It's solving for specific heat. So again, I have my heat. I have my mass. I'm solving for my specific heat. I have my final. I have my initial. Great. Subtract those. Multiply that difference by 125.6. And then 585 divided by that product is going to be 0.1390 joules per degree Celsius. Or, I'm sorry, per gram degree Celsius. Okay. We're going to move on to types of interactions. What type of elements are found in ionic compounds? Well, you can say metal or nonmetal, metal and nonmetal, I should say. Or you can list it as cation and anion. Okay, left side of the periodic table, right side of the periodic table, many ways you could list it. What types of elements are found in covalence? These are two nonmetals. Okay, both on the right-hand side of the periodic table. Determine if they are ionic or covalent. Okay, I always just look for the ionics, and what I'm looking for is, do I have a metal in them? If I don't have a metal, then it's going to be a covalent compound. So both, we got a fresh periodic table over here. Okay, sulfur and chlorine both on the right-hand side, covalent compound. Calcium, I know calcium is a metal, so that's going to be an ionic compound. I know potassium is a metal, that's going to be an ionic compound. Both of these are on the right-hand side of the periodic table, N and O, so this is going to be a covalent compound. Okay, draw the loose dot structures. So the steps of loose dot structure, I have to tally up my valence electrons. I distribute those valence electrons, I bond them to the center. Everyone wants octet rule, so everyone's going to want 8 valence electrons, except for hydrogen wants 2. So I'm going to add this up. I'm going to get 5 valence electrons out of nitrogen. I have 3 hydrogens, each have 1 apiece. I'm getting those numbers from here, valence electron. Okay, 5 valence electrons for nitrogen. Over here, hydrogen, 1 valence electron. Okay, so I have 5 from here, 3 total from here, so that gives me 8 total valence electrons. I have 1 nitrogen, hydrogen, hydrogen, hydrogen. I set it up in a symmetrical structure. I have 8 dots. I can make that 4 lines. I just divide it by 2 each line. I'll just do the dots. I'll do the dots on this one. I'll do the lines over this one. So I have 8 dots. 1, 2, 3, 4, 5, 6. So I've used 6 dots. I have 2 dots left. These hydrogens are all good because they only need 2 valence electrons. This nitrogen is not good because he has 6 and he needs 2 more. Well, good thing I only have 6 out here. I got 2 left. Now I have 8, so I'm all used. I'm good. Okay. I move over to this side with silicon and oxygen. Silicon, okay, is getting 4 valence electrons. Oxygen's getting 6 valence electrons, and I have 2 of them, so it's 4 from here plus 12 from here. So I have 16 total valence electrons. Divide that by 2 gives me 8 lines. Okay. Silicon's going to go in the center, so I'm going to make a symmetrical structure. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I used up my 8 lines. All right. The problem is silicon is not happy because he only has 2 lines. He needs 4 lines. So I'm going to have to move. I'm going to move 2 of these over here. So I'm going to end up with O, Si, O, double bond, like that. Okay. So now he has 4 lines or 8 electrons. He has 4 lines, 8 electrons. He also has 4 lines, 8 electrons. They're all full. Okay. Polar bonding is an uneven sharing of electrons. Okay. Uneven share of electrons, and nonpolar is an even distribution or even share of electrons. And that's it for that page.